Hello, this is lecture 18 for Physics 220. Today we're going to be talking about Gauss's law for magnetism and also some things about magnetic properties of materials. All right, so Gauss's law for magnetism looks a lot like Gauss's law that you're familiar with for electric fields. The difference is instead of having Q enclosed over epsilon naught, it's a big fat zero there because we don't have isolated magnetic monopoles. So no isolated south charges or north charges. We always have equal amounts of both. And so a magnet looks more like this. As we've learned, you can make a magnet with a loop of wire running current, or you can have some magnetic material, but you always have equal amounts of north and south. And so if you do a volume surrounding that and you integrate over the surface of that volume, you're guaranteed to have just as many field lines exiting the volume as entering back, so that you end up with the same amount of field lines going in as out. Okay, so just as a reminder, we had Gauss's law for electric field, and that was E dot dA has to equal the charge enclosed, Q enclosed, over epsilon naught. So if you had some positive charge, it would have some field lines going out, and so if you did some kind of Gaussian surface, a mathematical surface that you would choose out there and integrate over that surface, it would tell you something about the net charge that had to be inside the volume. But in the case of magnetic fields, it's just always zero in there. All right, now in the future, we're going to talk about a open surface. But in the case of Gauss's law, so this is the flux. We'll call that capital Phi sub B. So this is the flux through a closed surface. This little circle means closed. And something I forgot to mention, this Gauss's law for magnetic fields, that comes from the Biot-Savart law. So starting from the Biot-Savart law, you can prove that this has to be the case. So you get a lot of mileage out of the Biot-Savart law. You can tell that, or you can start with the Biot-Savart law and derive Ampere's law. You can also start with the Biot-Savart law and derive this Gauss's law for magnetism. So both of those laws you can get from that. They're not new physics, just new interpretation on the Biot-Savart law. The math is a little bit beyond what we want to do in Physics 220, but that's where it comes from. All right, so we're talking about a closed surface. That's what you need for Gauss's law. But next time we'll be talking about Faraday's law, and that one we also do a magnetic flux, but we do it for an open surface. So next time we will use magnetic flux for an open surface, or maybe we should say through an open surface. Okay, so here's our wire with some current going in it, and we have some magnetic field around it. So on this side of the wire you have magnetic field out of the page, and on the right side of the wire, it shows all these little X's, we have magnetic field into the page. And so what I'm talking about for the flux through an open surface, we could maybe consider this surface that I'm outlining here. This would be a little piece of that surface, a stripe right there. But we could integrate over all of the surface and find the total flux, and that would be an open surface as opposed to one that encloses a volume. So open surface. In fact, let's do that example to see how you would find the flux in this case. So this is an example. If I can get that to go. Okay. So in this example, we'll find the flux through this surface here, through inside of this square loop, due to the presence of this wire nearby that's creating this magnetic field. Now this is a non-uniform magnetic field. Okay, so what we'll do, and notice that I have an integral here without the circle on it, so phi sub b, the flux through that surface would be b dot dA. Okay, now let's suppose that our area vector, d area, points into the page. It should be perpendicular from the surface. You have two choices which way to do it, into the page. And so now we'll have, these guys will be parallel because our magnetic field is also into the page. So that's nice. Now, our B field is actually stronger close to the wire on this side, and it's a little weaker further out. And so we actually came up with a formula in a previous lecture. B, as a function of distance from the wire, is mu naught I over 2 pi r. Okay, so what we can do then is calculate this flux the following way. So those are parallel, so it's just B times dA. Now, let's think of a dA. What I'm going to do is maybe use this stripe here. Everywhere on that stripe is the same distance from the surface. So what I'll do for my dA, or from the wire, is I'll put the height, looks like that's labeled B. So height B times a thickness dr, that's this rectangle. There's an area that's all the same distance from the wire. And so now I can integrate from, looks like my wire starts at C and goes to C plus A. So I'm going to integrate from C up to C plus A to get that whole loop, or that whole square. Okay, but we have this interesting function here that we'll put in to our integral. All right, so we have phi sub b equaling C to C plus A, and then we have mu naught I over 2 pi r b dr. All right, so that's going to be mu naught b over 2 pi C to C plus A dr over r. All right, so this ends up being mu naught b over 2 pi, and we have natural log of C plus A over C, like that. Okay, so that is our flux. That is magnetic field times the area. But in this case, since the magnetic field was different strengths on different parts of our area, you would have to do it as an integral and add up all those contributions from all those little tall rectangles where the B field was the same on each stripe, on each rectangle. All right, let's do a few quiz questions. We have units for magnetic flux. So magnetic flux is B dot D area. Okay, what kind of units should that be? And the answer is B. You ought to have Teslas times an area. Okay. Choose a volume surrounding the negative end of an electric dipole. So maybe make it out of a couple of charges there. So we're going to choose this volume. One gets a situation where the net electric flux through that surface is negative. Oh, sorry, I just told the answer. Yeah, the net flux through that surface, it's all pointing inward, so that's negative. Okay. by choosing a volume surrounding the south pole of a magnet, one gets a situation where the net magnetic flux through the surface of the volume is negative, 0, or positive. So here we are on the south end of a magnet, and the answer is you're guaranteed for that to be 0. Magnetic flux through a closed surface, B dot dA, has to be 0. It's only through an open surface that it might not be 0. Okay. Gauss's law for magnetic fields is not useful as Gauss's law for electric fields because the surface integral has a different mathematical form. The magnetic field lines start and stop at infinity, or the answer is always 0, and that's the reason. It's always 0. So you can't get as much mileage as you can from the Gauss's law for electric fields, because you do have the situation where in some volume you might have a net charge, and that can be a useful thing to exploit to figure something out. Okay, let's do a top 10 list. These are top 10 things you don't want written on your job performance evaluation. So these are actual things that apparently somebody somewhere in the country had written about them in regards to how they were doing their job. These are what you don't want to have written on yours. So number 10, since my last report, this employee has reached rock bottom and has started to dig. Number 9, works well when under constant supervision and cornered like a rat in a trap. Number 8, this employee is depriving a village somewhere of an idiot. Number 7, he brings a lot of joy whenever he leaves the room. Number 6, a gross ignoramus, 144 times worse than an ordinary ignoramus. Number 5, if you see two people talking and one looks bored, he's the other one. Again, these are things you don't want written about you. Number 4, takes him 2 hours to watch 60 Minutes. Number 3, when she opens her mouth, it seems it is only to change feet. Number 2, gates are down, the lights are flashing, but the train isn't coming. And the number 1 thing that you don't want written on your performance evaluation is, this employee should go far, and the sooner he starts, the better. All right, let's talk a little bit about electron spin. So it turns out from scattering experiments, we think of electrons as being very much point-like, so very tiny charges. But the funny thing is, the spin of an electron gives, here's the true or false question, the spin of an electron gives no magnetic field because the electron is point-like. Is that true or false? And the answer is false. It does have a magnetic field. So it's kind of a funny thing to think about. And in fact, there's a magnetic moment. We've talked about magnetic moment before. We'll put mu sub b. It turns out to be the electric charge times h bar over 2 times the mass of the electron. And this gives a value of 9.27 times 10 to the minus 24 amps times meter squared. So the spin of an electron does come into play and give you some magnetic field. And in fact, some atoms have, well, many electrons, but oftentimes they're anti-aligned in such a way that their magnetic fields are canceling. But you can have some extra electrons that are not paired up, and so there's some net amount of magnetic field coming off of those atoms, like an iron atom. All right, so magnetic properties of materials can be quite interesting. In fact, the Earth's magnetic field that shields us from the sun's harmful solar wind comes from the materials in the Earth, most notably iron. So some things about magnetic materials. A lot of materials in the presence of a magnetic field can align the spin. So this is called paramagnetism, when the atoms will tend to have just some magnetic moment due to the electrons in them, and maybe also due to the nucleus in some random directions. But if you apply a strong magnetic field to them, they start lining up, a bunch of them, with the magnetic field, and that's called paramagnetism because it tries to line up parallel. Now there's some materials that will, the neighboring atoms kind of gang up and cause each other to align all the same, and you get these domains where a lot of neighbors are all doing the same thing, but other domains can be off in some other direction. This is ferromagnetism. Now you can actually put a strong magnetic field on the material and get a lot of these domains to switch, to orient with the strong magnetic field, and then when you take the magnetic field away, you've got all your domains kind of aligned the same way. And so then you have magnetized the iron, for example. Now, there's one more. So we've talked about ferromagnetism and paramagnetism. There's also diamagnetism, or materials that are diamagnetic, which is kind of interesting. You apply a magnetic field and they actually oppose you. So the atoms line up opposite the magnetic field. So that's diamagnetic. So you have ferromagnetic and paramagnetic, also diamagnetic. All right, which type of magnetism is involved in domains? So we have some pictures of domains here, and an external B field is being applied. So here's no field on the left, and then making a stronger field and even a stronger field, and we're seeing what happens. So which of these? And the answer is that's a ferromagnetic effect. All right, we'll see you in the homework help lecture.